Swayam Prabha. Digital India. Educated India.
Hello student, welcome back to the course on optimization methods for civil engineering. So today we will discuss a different meta heuristic optimization method, and that is your particle swarm optimization. This algorithm was developed in 1995 by Jim Kennedy. So he was in Bureau of Labor Statistics, US Department of Labor, and Ruth Everhart. So he was in Purdue University. So they have proposed particle swarm algorithm in 1995. So this is an algorithm for solving nonlinear optimization problem using particle swarm methodology. So we will discuss this particular algorithm. This is also one of the very popular optimization algorithm, meta heuristic optimization algorithm, and basically it can be used for solving a nonlinear non-convex optimization problem. This algorithm is inspired by social behavior of bird flocking and fish schooling. United we stand. So basically this is a group activity, and they basically they are when the birds are trying to find food. So whatever process they are following, so that is artificially simulated for finding an optimal solution of an optimization problem. Suppose a group of bird is searching for food in an area, and only one piece of food is available. So that is the solution of that particular search process. The birds do not have any knowledge about the location of food. Okay. So they do not have any knowledge about the location of the food, and however, they know how far they are from the food from their present location. So what is the best strategy to locate the food? So best strategy is that you follow the bird nearest to the food. So what they are doing, they are trying to, or they are communicate each other. So the bird has the information about his position, how far he is from the food. Similarly, they also have the information about the location of other bird, and then the best strategy, and therefore the best strategy is to follow the bird nearest to the food. Suppose this is the current position of a flying bird. A flying bird has a position and a velocity at time t. Okay. So this is the current position. So he has a velocity and he has also a position. In search of food, the bird changes his position by adjusting the velocity. So velocity means he will change his speed as well as his direction. The velocity changes based on his past experience and also the feedback received from his neighbor. So what he is doing, a bird is doing, so he is changing his velocity based on his past experience. So he actually he has the memory. So he is storing all his past your location, that means past based location, that is his personal experience he is storing, as well as he is also getting the information from his neighbor. Okay. So therefore he is changing his location, or he is changing his position based on his past experience and also the feedback received from his neighbor. So based on that, he will change his position, and this will be the new position of this bird. So basically from here to he is moving up to this location. So this search process can be simulated artificially for solving nonlinear optimization problem. So this is a population based stochastic optimization technique inspired by the social behavior of bird flocking and fish schooling. So, this is a population based algorithm. So, just like classical optimization algorithm. So, we are not going from one solution to another solution, but we are actually taking a population and we are trying to search in multiple direction. So, this is again stochastic method. So, this is not deterministic, and then as I said that this is inspired by the social behavior of birds flocking and fish schooling. So, here each solution is considered as bird, we call it particle. So, this is the solution. All these particles have fitness value. The fitness value can be calculated using objective function. So, what we are doing here? So, we call the solution as bird or we call it particle, and for each particle I can evaluate his position by using the objective function, that means how far or what is the quality of that particular position or particular solution. So, that can be calculated using objective function. All the particles preserve their individual base performance. So, that means they have the memory. So, what they are doing, they are preserving their individual base performance, that means base location they are preserving. They also know the base performance of their group, that means they can communicate each other. So, these are two qualities. So, one is that they have memory, so they are preserving their base performance, and second one is they are also aware about the base performance of their group, that means they can communicate each other and they are aware about the group performance. They adjust their velocity considering their base performance, that is his personal base, and also considering the base performance of the base particle. This is the flow chart of particle swarm optimization algorithm. So, we have initialized the population, and then next step is that we will evaluate the fitness of each particle. So, we are initializing the particle, then we are calculating the fitness value of each particle, and then we are modifying the velocity based on previous based and global based position. Then we will check the termination criteria. If termination criteria is satisfied, then it will terminate, otherwise it will go to the next iteration. So, this process will continue until we are not satisfying the termination criteria. So, once it is satisfied, then you will basically declare the optimal solution. So, here basically we are using two equations. One is to update the velocity. So, velocity is updated something like that. So, this is the current velocity of the previous location, and this is the updated velocity. So, which is equal to omega v I, then plus c a random number, and then this is P b is the personal based, and this is the x I, that is the current location, and similarly C 2 multiplied by a random number, then a global base minus x I is the current location. And once you are getting the new velocity, and then we can calculate the new position, and which is equal to x I plus v I plus 1. So, this is the previous location. So, this is the new location, and new location is x I plus v I plus 1. So, here this is the inertia effect, that means before taking a decision, suppose the particle or the bird has taken a decision to change his velocity, and but due to inertia effect. So, he will move some distance. So, this is the inertia effect, and this is basically give you the direction towards his personal base. So, therefore, you can say this is local source or personal influence, this part, and the other one is the global source or basically the social influence. So, here G b minus x I is giving you the direction towards the base particle, and P b minus x I is giving the direction towards his personal base. So, therefore, this is a combination of local source. So, this is you can say local source, and this is your global source. Okay. And anyway, so this is the inertia effect. So, as you have seen, this is a very simple algorithm. So, it can be implemented easily. So, with few lines of code you can implement this particular algorithm, and as I said, this is one of the most popular and powerful meta heuristic optimization algorithm for solving nonlinear optimization problem. So, here C1 and C2 are the learning factor and omega is the inertia factor. So, therefore, suppose you want to, so or you can say that C1 and C2 are basically step length. If you are using large value of C1, so you will give a big jump, but if you are using smaller value of C1, that means you are basically searching near that particular solution. So, I can actually give suitable value of C1, C2 and omega and can control the search process. Suppose this is the current location of a particle and this is his personal best. So, that he has preserved this location personal best performance, and this is the global base performance, or you can say the base performance of the group so far. And now, suppose your velocity at this location is V I. So, therefore, how he will adjust the velocity or how he will go to the next location. So, this is the effect of inertia. So, because of inertia, so he will initially move in this direction and then he is going towards his personal base direction, and this part is coming C1 ran then personal best minus xi. Okay. So, this is his personal base and this is basically omega V I. Okay. So, this is the inertia effect, and then he will move towards the global base. So, this is basically C2 ran is GB minus xi. Okay. So, this is your GB. So, that is GB minus xi. So, and that will be his new location, that is x I plus 1. So, what are the steps of this algorithm? So, step 1, so we will create initial population of Sn uniformly distributed over the search domain. So, I can use any uniform distribution to generate this population, and once I am getting this population, we will evaluate the position of the particles according to the objective function. So, I can use any fitness function, and fitness function is basically you are getting from the objective function, and you can evaluate the particles. And so, whatever new position you are getting, if the current position of a particle is better than its previous base position, that is the personal base. So, we will update his personal base position. So, whatever new position you are getting, that is x I plus 1, if this position is better than his previous personal base position, so we will update that one. So, we will update his personal base position, and then we will determine the base particle of the population, and we call it global base. Okay. So, this process will continue unless and until we are not reaching the termination criteria. Once we are reaching the termination criteria, so we will stop the iteration and the final solution will be displayed. Now, how many numbers of particle you should consider? So, usually consider between 10 to 50. So, number of particles, so you can minimum 10 you can consider, and I think 50 is sufficient in this case. And C1 represent the importance of personal base value. So, as I said that by C1 I can control the step length. So, that will represent the importance of personal base value, and C2 represents the importance of neighborhood base value, that means the importance of the global solution, and generally C1 plus C2 is around 4. So, you can consider that C1 equal to 2 or C2 equal to 2 or C1 equal to 1.5, C2 equal to 2.5, something like that. So, summation should be around 4. So, when the velocity is too low, the algorithm is too slow. Okay. So, velocity is less means the algorithm is too slow and you may need a lot of iteration to reach the optimal solution. On the other hand, if velocity is too high, the algorithm will be unstable. So, in that case it will be unstable. So, therefore, you have to choose this particle in such a way that velocity is neither too slow, in that case it will take a lot of time, or neither it is too fast, in that case the search process will be unstable. So, unlike genetic algorithm, then other meta heuristic algorithm we have discussed, suppose ES. So, PSO does not have selection operator. So, as you have seen, so we do not have in PSO does not have any selection operator. That means, you are not deleting any particle. So, what you are doing basically you are trying to get his new position. So, you are not deleting any particles and therefore, we do not have any selection in PSO. PSO is the only ES that does not remove candidate population member. So, as you have seen, so we are not removing any solution. So, only we are updating his position. PSO combines local search. So, as you have seen, so we are also giving importance to his earlier base performance, that is the personal base, as well as global search. So, PSO combines local search method with global search method, attempting to balance exploration and exploitation. So, the algorithm is very simple in concept, as you have seen, the algorithm is very simple. So, what we need basically, so we need only two equation to update the velocity and then we are updating the position. So, it is a very simple algorithm. I can show you that this is a very powerful algorithm in finding global optimal solution of a function, and it is easy to implement. So, the code is very simple and computationally efficient. So, this is all about particle swarm optimization. So, as you have seen, the algorithm is very simple in concept. We can implement this algorithm with 10 to 15 lines code. So, you can write a code in either MATLAB or your R program or any other language. Okay. So, you can use any other language, but here in this particular course I will solve some problem using the PSO package available in R. So, here I am not writing the code. So, directly I am using the PSO function available in R to solve the problem. So, let us solve some problem using R. So, I will use PSO algorithm here. So, for using PSO you have to install the PSO package. So, as you have seen, so this is you have to do only for the first time. So, you have to install this one. So, I have already installed in my computer. So, I will not install it again. However, if you have not installed this thing, so you please install first. So, you can write install.packages and within quotes you can write PSO. So, this will install the PSO package, but you need internet connection to install that one. So, I have already installed. So, therefore, I will not run this particular line. The next step is to include the library. So, let us include this library, that is your PSO library. So, now it has been included. So, I can see actually. So, here the function is PSO optim. So, let us see this function first. So, I can go to help and then I am writing. So, this is PSO optim, and then you can see this function here. You can see this. So, this is particle swarm optimizer. So, this is the function PSO function. So, what you have to do here? So, the function name is PS optim, and here you have to define the parameter. That means just like the classical method. So, you can define the initial solution because this is a part of optim package. So, in case of classical method, so we generally define an initial solution. So, in order to make it similar, so in PSO algorithm, so the provision is there, you can define an initial solution. So, in that case what will happen, the particle will be generated near to that solution, but that is not mandatory. So, you can also define the number of variable only, that means I can define NA, that means I will not define the initial solution, but I will define the number of variable. And next is you have to give the function name, and then some gradient information and all those things you can put, but if you are using the hybrid method, and basically you have to define lower bound and upper bound, and finally there is some control and you can list it, the control parameters here. Okay. So, what I need basically, so I have to define this function fn, and I have to define lower bound and upper bound, and I have to define the parameter. So, it has been defined here what is parameter, what is fn, what is gr. So, if you are using hybrid method, a function to return the gradient if local source BFGS is used basically. So, by default it is null, and then you can define what is lower bound, what is upper bound, and you can define the control parameter. So, you can see the details. By default this parameter has been defined, but you can also define it to if you want to sense those parameters. So, I will show you how you can sense this parameter, and here you can define maximum number of iteration, then maximum number of function evaluation you can put, actually that maximum iteration I can put by default it is your 1000, and by default it is infinity, maximum function evaluation is infinity, that means it can go up to any value, and similarly other parameters you can define. Okay. So, generally I would like to define what is Cp, that is basically C1, and Cg, that is the your C2. So, this is local exploration constant and this is global exploration constant. So, in my presentation, so I have written this is C1 and this is C2, and similarly you can also define what is Vmax. Okay. So, these are some of the things you can, and you can also use hybrid. Okay. So, you can also use hybrid method. So, hybrid method is something like that. So, as you have seen, so whenever you are applying the genetic algorithm or any meta-heuristic optimization method, so we are not calculating the gradient of the objective function as well as constraint function. So, therefore, what may happen, so this algorithm may not give you the exact optimal solution, but it will give the near optimal solution. So, you may not get the exact optimal solution where gradient is 0, but you may get a solution which is near to the global optimal solution. So, in that case what you can do basically, so you can apply the classical method. So, classical method is using gradient information, and you will get the exact optimal solution. So, we call it hybrid optimization method, that means initially we will apply PSO and then we are applying classical optimization method. So, in this case we are applying BFGS algorithm, that is for local source. Okay. So, I can also define that one. So, and these are some of the control parameter you can see, and they have also given some example. So, for particular this function they have shown you the example. So, anyway, so let us discuss this thing, this particular problem. So, first I will solve the function 1. So, what is function 1? So, maybe I will mark comment this one. So, this function 1 is x1 square plus x2 minus 11 whole square plus x1 plus x2 square minus 7 whole square, and this is between minus 5 and plus 5. So, let us execute this particular line, and then let us execute x1 x2 values, then I am calculating the z values, then I am plotting the contour. Okay. So, I am getting this contour. Then this part is just to plot the function. Okay. So, this is not part of PSO algorithm. So, I am just plotting this particular function, as you know. Now, I have to write this function in this order in order to apply PSO. So, I can actually write an x, and within x basically I have two variable, that is your x1 and x2. So, this function I am not using, second function. So, first function I am using. So, let us execute this particular function, and then here I am using seed value 1. So, this set seed value we are doing just to get the same result. Okay. So, this is you can use, or if you are not using, you are not getting same result. So, let us execute this thing, and then I am using PSO optim. So, what we are doing here, I am defining the initial point, that is 2 and 2, but as I said that you may not define. So, just like here, suppose we can also write that NA 2. So, if we are writing, we may not define, this is NA and this is 2, that because we have two variable here, and lower bound is -5, upper bound is +5, and the function is f. So, this function f function I am using. So, function is f, and in control this is the absolute tolerance I am putting, that is your 1 e to the power -8, this is the tolerance I am putting, and then Cp I am putting 0.5. So, I may define or I may not define. If I not define this value, so Cp and Cg I may define or I may not do that. So, if we are not giving that one, the default value will be taken, and hybrid off. Okay. So, I am not using any hybrid. So, you can, so it is off basically, or you may not write this thing. So, if we execute this particular line, so it will execute the PSO algorithm. So, we are getting the solution, you can see that one. So, we have executed this one, and then so let us plot these particular points over this contour map. So, let us execute this one. So, I am getting this solution, okay, and the point is this one 3.584421, and this is minus 1.848124. Okay. So, what I can do basically, so maybe I can execute this one. So, every time I should get the similar result. So, let us see, yeah. So, you just see I am getting the similar result. If I am not executing this one, or if I put a different number, let us see, I am getting the same result. So, let me start it again. So, this time I am not defining this one. Okay. So, let me execute from here. So, this is the function, and so I am getting this solution again. So, I am getting this particular solution. Yeah. So, this time you just see I am getting this solution, and if you, so this solution is 3 2, but I am getting 3 and 3.007 and 2.00 something like that. So, what I can do basically, so I can also use hybrid. Okay. So, if I use hybrid, then suppose this is hybrid on, then so I am getting this solution. So, in that case what will happen, there will be some refinement. So, what you will do basically, if you are getting near optimal solution, then after that if you are applying classical method, so you will get the exact optimal solution of the problem where gradient is 0. So, I hope this is fine. So, let us try with the next function. So, I would like to clean this part. So, I will delete the history. Similarly, I will also clean the console. So, now let us execute the second function. The second function, if you plot it, so this is a very complicated function, as you have seen earlier also. So, here the solution is somewhere here 0 0, this is the global minima of this particular. There are several local optimal solution. So, and global solution is somewhere here at 0 0 and function value is 0. So, we will try to find out this solution using PSO algorithm. So, I am using PSO now, and so let us execute this particular line and then apply PSO. Okay. So, you are getting this global optimal solution. Let us see what is this solution, and solution is 0 0, but you are getting 10 to the power minus 11 or 10 to the power minus 11 is exactly exactly not 0, but it is near 0. Basically, both x1 and x1 and x2 are 0, and function value is also near 0. So, what I can do basically, suppose if I write off, then what will happen? Just see. So, this time I am getting this is 10 to the power minus 6 and 10 to the power minus 7, but if you are using hybrid. So, you are getting little bit better solution. So, as I said that I can change these things. So, CP right now I am putting 0.5 and 0.9, but I can use as per that rule. So, I can use 2 and 2. So, it should be around 4. Okay. So, 2 and 2 I am using. So, in that case just see. So, if you are executing this, yeah. So, I am getting this value, and I can use suppose 1 and 3 also I can use, just see. Yeah, so, I am getting this thing, and if you are putting this is hybrid on, and then you will get little bit better solution. Yeah. So, it is coming 10 to the power minus 11 and 10 to the power 9. So, you can improve your solution using hybrid optimization technique. The idea is that for this particular problem. So, if you are using classical method, so you will not get the global optimal solution. So, you will only get a local optimal solution. So, therefore, idea is that initially you apply a meta heuristic optimization algorithm just like genetic algorithm, PSO, then we have also discussed ES, evolutionary strategy. So, and you can apply any meta heuristic optimization method. So, in that case you will get a near global optimal solution, that whatever solution you are getting, that may not be exactly optimal solution, global optimal solution, but it will be near the global optimal solution. So, after that you apply any classical method or any local source technique to find out the exact optimal solution of the problem, and this is known as hybrid optimization technique. That means, we are using two algorithms. So, one is that meta heuristic optimization algorithm, and then we are applying the classical method. So, as you know that once you are applying classical methods, so classical methods are using gradient information. So, therefore, you will get a solution where gradient is near to 0 basically. So, it will never be 0, but it is a very small gradient. Okay. So, this is the way I can solve a nonlinear non-convex problem with several local optimal solution. So, we can find out the global optimal solution of this problem. The problem you have seen, this problem has several local optimal solutions, and one of them is the global optimal solution. And basically if you apply classical method, so you will never get this one. So, you may get it, but by changing the initial solution, but once you are taking a initial solution near the global optimal solution, then only you will get the global optimal solution. However, if you are applying PSO first and then classical method, so you will get the global optimal solution of the problem.